Okay, so I could just start if that's okay. So hello, my name is Rohan Arunkumar. I'm a rising junior. I go to high school. I'm from New Jersey. And last year I made a project called GreenMiles, and it was utilizing deep learning to analyze vehicular carbon emission trends in urban areas like Jersey City. So I made this project because I read a statistic in my driver's education class, and it told me a simple statistic, like we've all probably heard this before, that year by year our purchase of vehicles just keeps increasing. But I was intrigued by this and I was thinking like, with the ecological mind that, well, how is the carbon dioxide doing? That must be increasing as well, right? The more traffic that we have. So I searched the web for existing calculators. However, all of them were very similar. So they let you search the car by brand, and it only told you the CO2 associated by brand. So it wasn't actually talking about like how the fuel type affects CO2 or how engine size affects CO2, but rather how does Toyota affect CO2? How does Nissan affect CO2, etc. So I noticed that gap and I was interested in machine learning at the time. I've done a project at the time. So I wanted to see if machine learning could actually identify associations between carbon dioxide and vehicle car settings. So as an introduction to the problem, well, reducing vehicle emissions is essential for mitigating climate change and improving air quality because as the years go on, the cars continue to be manufactured and the emission levels continue to go up. So why did I pick this problem? Because again, most consumer carbon dioxide emissions calculators are based on brand and mileage, but they never really analyze car settings, right? They don't talk about fuel type or fuel size, engine size. So I wanted to investigate if machine learning could isolate and quantify these configurational level effects, especially in urban areas. So for that, I asked myself the research question, to which extent can machine learning models accurately predict vehicular carbon dioxide emissions using configuration level attributes? And as an extra question, which one of those features actually matter the most? So in other words, which one of these features can we change in order to reduce our carbon emissions? So in order to do this, I conducted a methodology that's normally very standard for a machine learning project. So in machine learning, you could treat it, and nothing on the slide is related at this point yet, but machine learning works as a kind of input to output framework, and we have an input with a black box, and it goes to the output. So I learned from previous projects that the input section is often very rushed, but it is the most important part. And actually, one of my AP chemistry teacher always says garbage in, garbage out. So if we have bad data, then the results are going to be bad as well. So the very first steps, although they're typically undermined, they should be taken very seriously. So I did learn that from my previous projects. And so I wanted to make sure that the data I used for this project was very accurate and there was a lot of it. So there is an open source data set from the Canadian government, and they have exactly what I wanted for a data set for this type of project. So we have specific car settings, such as you can see here, the engine size, transmission, fuel type, and fuel consumptions. So these are different types of fuel consumption. This is the highway, and this is total. This is city, and this is country. And then these are the features, right? So it's like how does engine size, cylinders, transmission, fuel type, and fuel consumption affect carbon dioxide emissions? So these columns are the input, and the last one is the output. So this is credible data because it comes from a reputable source, the Canadian government, and it can accurately predict carbon dioxide emissions. So what I did with this data is I split it up into 80% training, 10% validation, and 10% test, where 80% is kind of like the homework for the model, or rather the lessons. So it does 80% learning, so it's learning about this data over here. And then 10% validation is kind of like homework, it's getting practice from that data set. And the last 10% is like a test. So it's like, how accurate are you now? I want to know how accurate you are. So it takes 10% of the data rows and it tries to predict the CO2 emissions. And based on how good it is at doing that, the model's accuracy is found. So I used three models to do this. They can be seen at the bottom. I'm not sure if you can see my cursor. However, we have the bottom left here is K nearest neighbors, and that predicts it purely on distance. So the new example to classify is put as a question mark, and the closest class to that is what it's going to be predicted as. So, for example, if we have an engine size of 3 and that correlates to 100 grams CO2 emissions, then if you have an engine size of 4, you can just do the math. So it'd be 133 grams of CO2. So it's kind of like a number correlation model to oversimplify it, to say. Random forest is kind of like a human decision-making model. So it takes the data, splits it into subsections. So let's say we have one subsection as fuel consumption and then one section here and another section here. So it just splits that into 3 sections and then it finds the results for each. But again, I'm oversimplifying here. And then MLP is actually the most intriguing one, in my opinion, because it works exactly like the human brain does. It's what we call a neural network. So as you can see in the image, we have many quote unquote neurons. They're circular objects and they have weights. And what these weights do is that they update the number associated with each neuron until you get to the end. So it's like a mathematical framework where the model just keeps learning from each row and it updates the numbers. So it goes from one layer of the brain all the way to the end. By the time we reach the end, we know the correct number. So that's MLP. And I hypothesize that MLP would be the best because it's the most complicated, it takes the most time, and it's the most accurate. Okay, I'm not gonna go there yet. I just have so feature importance was also done to determine which car settings are most influential for emissions. So for example, what a feature is it just means input. So it's columns 1 through 8 here, excluding the CO2 emissions column. So what feature engineering does is it tries to predict which column matters the most in predicting CO2 emissions. So that was done. So the results of this feature importance can be seen here on the top graph. So all of these columns here, and based on which one has the most importance, that means that is the most important for vehicular carbon emissions. So the most important things for carbon emissions was the fuel consumption. And then the second most important thing was the type of fuel. So the type of fuel actually had a considerable difference here. So we have fuel type ethanol, fuel type premium gasoline, fuel type gasoline, and then fuel type diesel. They're encoded as letters. But the most important one is ethanol because according to this graph, it had 0.15 importance. So what ethanol actually does, like upon looking at the data set more carefully, ethanol, when you use ethanol gas in a vehicle, is associated with 15% lower emissions normally. So that's one interesting thing that the model found. Model also found that using diesel gas is 5% worse for carbon emissions. But I'm going to show a demo of the website so that makes more sense outside of the context of the graph. And according to the results, the main thing to see here is that the MLP neural network model had the highest R score. It was 0.996. So therefore, that is the best model. So why do the results matter? So the models were good. The feature engineering showed that fuel type was the best. But the results matter because environmental decision making requires people to actually understand what they're seeing. So we need to understand how exactly the factors matter. So a model can be accurate and still fail to answer the question. That's why I conducted feature importance to see which specific inputs actually are the most important for the output. So this project showed me that the question, how accurate is the model, is just as important as the question, what is the model actually telling us? And we can see this in the demo, which I have here. So I deployed my model using Streamlit because the ulterior goal, not the ulterior, the ultimate goal of this project is so that users can actually use the website. And before they purchase a car, they can try to make the best choice to reduce their CO2 emissions. So they can modify these values here shown in the right image. They can play around with the values and see which values actually result in the least carbon emissions. And normally, right now, the fuel type it says D, but if I were on the website and I changed it to E, then the carbon emissions they would see is lower. So they would actually purchase a vehicle with ethanol fuel instead. So they can make decisions like these by playing around with the model. And it allows them to understand how exactly their decisions are affecting their CO2 emissions, right? So they can try to reduce their fuel consumption, change their fuel type to ethanol, reduce their engine size, and other options like this. So that's the entire point of the project is to build a machine learning model so that users can understand how their choices are affecting carbon emissions. So, a few technical things that I learned and I think is very worth mentioning is I learned that nonlinear models like the MLP can work under correlated inputs. So we can actually go from X to Y. We can see how inputs result in a given output, in this case, carbon emissions. And that deployment reveals weaknesses theory because when deploying it, right, we can see how exactly each condition, impacts the output. We can see that ethanol reduces by 12%. If we just looked at the model accuracy, we would not know that. We have to look deeper. So that's what this project mostly taught me. In the future, I think the most important thing I want to do is bullet point two over here, and it's to expand the data set. Like I mentioned, the data is currently from the Canadian government. But if I wanted it to be more accurate and work in all regions, it would be good if I could gain access to data from countries like the United States, or any other countries in the world. So uh also I want to do a deployment as a public tool. So I want this to be accessible to more people. And one of the great ideas that I had, and I'm working towards doing that, is actually using this in car checkout systems so that when people are actually buying a car, they can use this tool and make the best choice, the greener choice. In conclusion, GreenMiles demonstrates that machine learning models can effectively predict emissions, but it also showed me that we have to look deeper sometimes than the model itself. We have to see which inputs are best for the output. And that's the biggest takeaway I have from GreenMiles. So yeah, thank you.
Thank you so much, Rohan. We can step towards the questions, and I do want to congratulate you that this is an amazing project. If we have time, we can step towards questions.
Mm.
Amy, do you want to take it off?
We have time if you want to go ahead and start nearby because our next person is not here. So we have time for questions.
Sure. Amy, would you like to start it off, or can I?
You can go ahead if you have something, go ahead.
Sure. I think your project was very clear in your data set, and I really appreciated that. And it really showed the depth of how to not only consider the model R square or accuracy, but also analyze the physical plausibility of the results. And that's a very important thing. My next question would be, d how generalizable do you think the model is to other cars in the United States? Because I think we touched on this in the presentation, but could it could it be the same as those in India? Since there are many more make and models and fuel ICE engine types in places like India, right? That would
Yeah,
be
yeah.
my question.
That's a very good question. Yeah. And that's also one of the like major limitations that I hope to address. And I think it's kind of like something where like the model itself can this project was made to address the gap that, like, like you mentioned, the make and the models are mainly what's being focused on in CO2 calculators. And so I just wanted to step into like how exactly can a user make choices in like the car settings that can actually reduce like carbon emissions. So I think like you mentioned, like for a car in India, I still think like if you swapped out for ethanol gas, you'd still have less CO2. If you had less cylinders, you'd have less CO2. So I think like the generalizability of the model should work for other regions, but like I said in the future work, I do want to expand past the Canadian data set. But there is no other open source data, that's the only issue.
Sure. Amy, do you have one? Or
I'd just like to congratulate you on a wonderful presentation. It was a lot of great information and a lot of data points. How long have you been working on this?
Yeah, I worked on this for around 6 months. It was my science fair project at the time. I was just really interested in like trying to see how we can spread awareness about you know, these issues, especially with like vehicles, because a lot of people just make decisions based on the make and the model rather than the exact configurations. So that's why I made this project.
I think that's great. I think you're absolutely right. Do you think it made a difference?
Yeah, I think it did because I actually did demo it for the science fair and I do hope it reached people. Of course, that's another future step. If I could get it into car checkout systems, it would definitely reach a lot more people. But the initial phases, like I had flyers in my community and I did see a lot of traffic on the website. So I do hope that it did reach a lot of people. But I think if it's used in car checkout systems, it could make a big impact.
Right.
one last question on my end. Uh, what would be your plan if you're making the AI model customary for these car checkout systems? Uh, what specific actions would you take? Like, let's first uh, center this to one province in Canada because your data set was in Canada.
Mhm. Yeah, so I think the steps, it's not much different than like deploying it on the website itself. It's, I'm not sure if you remember the image I had on the deployment slide with like the sliders, but I think it would be like really similar. Like in car checkouts, they normally let you customize your car build. So it would be like those similar sliders. There could be two options I could take there. I could either retrain the model on the sliders on the actual checkout, or I can use the model settings. But either way, it would just be like the same thing as the website, but it would be on the car checkout. So users can like drag, like for example, fuel type, engine size, and they can play around with it and they can see which one is the best for carbon emissions. And they can balance that with their own preferences. So it can be something in the middle if they want to be a little better for the environment while also keeping something that they would like. So yeah, if that makes sense.
That makes a lot of sense. Thank you so much. You did a brilliant job in your project.
Thank you. I appreciate it. Yeah.
Thank you so much, Rohan. We appreciate you sharing today.
Yeah. Thank you. Have a good day.